So it's a pleasure to have here Eduardo Provenzi from the University of Bordeaux, and we will talk about color perception and quantum information viewpoint.
Okay, thanks Matteo, thanks Maria Stella for inviting me here. I hope that everybody can hear me. I will introduce a modeling work about color perception that I've been doing with Michel Berthier from the University of La Rochelle since 2018. So it's a little bit difficult to condensate 5 years of intense research in, I don't know how much time I have, 45 minutes, 50 minutes, something like that. Yes. Okay, but I will try. So the summary, the outline of my talk is this one. I will start introducing the Schrödinger axiom, which is the highest point of colorimetry, theoretical colorimetry during the first half of the 20th century. And then I will talk about the Resnikov revolution. He did a splendid work in which he revolutionized the way we deal with color perception. And then I will introduce our inspired quantum model that will give us the opportunity to formalize both Newton's color disk and Herring opponency. And then I will talk about more recent work that we have done about quantum measurement and quantum information. And I will finish with future perspectives. I don't know what happened. Okay, that's cool. So let's start with the Schrödinger axiom. And in the beginning of the 20th century, the situation, the knowledge about color perception was very fragmented. And works from Riemann to von Helmholtz, Maxwell, and Grassmann told us that the set of color sensation is not a simple collection, but is a mathematically structured space with a beautiful mathematical structure. However, nobody had a theory that was able to put together all these known facts about color. And if you think about it for 1 second, it's exactly what happened to Maxwell 50 years before, with all the knowledge about electrodynamics and magnetism that we didn't know how to put together. And Schrödinger did something that is really similar to what Maxwell did. I don't have time to talk about why Schrödinger arrived to this kind of statement, but please trust me, he arrived to say that the space of perceptual colors, when I talk about perceptual colors, it means that we deal with colors that are perceived by the human visual system and not physical colors, so not spectra of wavelengths in the visible spectrum, but perceived colors by humans. So the space of perceived colors is, by an ideal trichromatic observer, is a convex cone, regular and three-dimensional. So mathematically speaking, we know what this means. If I had to talk about all the experiments that allowed us to arrive here, I would need another hour. So let's accept this statement, and let me tell you why this set of axioms is not sufficient, is not satisfactory. There are 2 points of view. 2 reasons why this is not satisfactory. A mathematical reason is that these properties are not enough to set a specific color space. Too many color spaces fit these choices. And there are also perceptual reasons that are striking. In the first part of the 19th century, here you can see a section of the retina. People tried to understand if Young hypothesis about the existence of 3 photoreceptors that nowadays we call cones sensible to the wavelengths corresponding to blue, green, and red was true or not. And so all these experiments start from the need of testing the trichromacy hypothesis of Young. At the end of the 19th century, there was another revolution that was proposed by Herring, and Herring, on the simple basis of, if you want, philosophical thinking that there are colors that cannot coexist at the same time, for example, red and green and blue and yellow, you cannot perceive reddish green or bluish yellow. And so starting from this thought, Haring proposed a theory called opponent color theory that did not fit together with trichromacy. So there were these two theories, trichromacy and Haring opponency, that seem to be incompatible. But nowadays, we know, let's look again at the section of the retina. We know that this is a very important discovery of the 20th century, that there are ganglion cells. And ganglion cells, what they do is to support Haring opponency. So we know that trichromacy and Haring opponency are not two opponent theory, but they are two complementary theory. And if we want to understand human perception about colors, we have to deal with a mathematical theory in which both trichromacy and Haring opponency are contained in this theory. I will show you that the quantum model allows us to cope with trichromacy and also Haring opponency. Let me go through Reznikov revolution. As I told you, the mathematical part is not, regarding Schrödinger axiom, is not enough because too many color spaces fit the choice. And in a beautiful, very beautiful paper called Differential Geometry and Color Perception, published on the Journal of Mathematical Biology in '74, Reznikov, he was an harmonic analyst. He showed that there exists a transitive group action on the space of perceived colors. And so it made it a homogeneous space. So we can complete Schrödinger axiom by saying that C is a homogeneous, convex, regular, three-dimensional cone. And thanks to classification theorems about this kind of spaces, we know that there are not infinite possibilities for this kind of space, but just two. The first one is this very simple space that is a flat space, is the Cartesian product of R plus with itself 3 times. And this is a flat space that is exactly the mathematical space that is used by the CIE. The CIE is the Commission Internationale de l'Éclairage, which is an entity that self-declares to be let's say, only entity who can deal with colors and illumination and reflectance, etc. Very humble. And in our opinion, they do disasters when they talk about color perception, because all the spaces that they produced are flat. Are these kind of, mathematically speaking, they are dealing only with this kind of space, which is not satisfactory for many reasons when we talk about color appearance. When we talk about color reproduction, we are using RGB spaces in this moment. So for color reproduction, so for reproduction of color stimuli, they are nice, but not for explaining appearance and perceptual phenomena. This is something that many people do not understand. One thing is to reproduce color stimuli, and this is nicely done by these spaces. Another thing is to study color perception. There are two different things. And luckily for us, Reznikov showed that there is a second possibility that came out of this completed Schrödinger axioms with the homogeneity axiom. That is this space here. This space is not flat, it's curved, and it is the Cartesian product of R plus, and the second part changes completely. It is a hyperbolic space of constant negative curvature, -1. And since, as I told you, he used group actions, it is not surprising that the model, the hyperbolic model that appeared in his paper was SL2R quotient SO2. But for our seminar, it's much better to use other hyperbolic models. In particular, this model here, that is the space of real positive defined symmetry 2, and the three-dimensional future light cone. This is not the future light cone of special relativity, because it is embedded in the three-dimensional Minkowski space, not in a four-dimensional Minkowski space. There is one dimension less, of course, because we're dealing with a three-dimensional space. So these two spaces will appear many times in the rest of the seminar. Yes?
So, just to say, this is not about the number of parameters you use, right? It's about metric.
I didn't introduce any metric.
Then when you say curve, what does it mean?
Sorry, you mean the intrinsic, yes, the intrinsic curvature of the space. But I mean,
How is it related to perception?
it is related to perception because when you want to talk about, for example, color differences, you have to introduce metrics that are coherent with this geometry. Yes, if you want to go there, you are absolutely right. So the nature of the geometry of the space will tell you what kind of metrics you are allowed to put on. Yes, and in fact, Reznikov studied a lot metrics based on Poincaré geometry. But we are using Klein geometry, so it's a different thing. And just because the question is very interesting, one of the first real-world application of differential geometry as introduced by Riemann was done by Helmholtz, who used Riemannian elements in order to study color differences. So thank you for the question because it's very interesting. So this already showing that only two spaces with the two different geometries, one flat and one curved, fit with this new axiom is already enough to consider the work of Reznikov one of the most important mathematical works about color. But in the final part of his incredibly beautiful paper, he used one thing that is paramount important for our model, because he fused these two models in just one model related to Jordan algebras. And Jordan algebras were introduced by Pascual Jordan, a theoretical physicist, in 1932, in the setting of algebraic formulation of quantum mechanics. And in order to understand how Jordan algebras are related with these two structures, let me just introduce you in a nutshell the structural properties of Jordan algebras and their relations with positive cones. So first of all, Jordan algebra is a vector space endowed with a commutative and bilinear, but not necessarily associative product that satisfies this relation here. And this relation allowed Jordan to introduce and build powers of elements of this Jordan algebra, which is absolutely not evident, because if you don't demand associativity, then it's not easy to build powers. So with this request, you can build powers. The Jordan algebras that are interesting for our applications are called formally real. Formally real Jordan algebras verify this property here, and as you can see, this property is reminiscent of the same property of real numbers. This is why we call these Jordan algebras formally real, because formally they behave like real numbers regarding this relation, of course. It is possible to show that every formally real Jordan algebra has a unit, has a scalar product, and can be endowed with a partial order. So if we have a partial order, we can talk about positive or non-negative elements. The set of non-negative elements of a formally real Jordan algebra is called the domain of positivity, and the topological interior of the domain of positivity is called the positive cone. And this is where we have the relationship between Jordan algebra theory and the two spaces that Reznikov put in evidence, because it is possible to show that every positive cone of a formally real Jordan algebra is a symmetric cone. What is a symmetric cone? Is an open, convex, regular, homogeneous, and self-dual space. Self-duality is written here. So apart from self-duality, we have exactly all the properties that appear in the Schrödinger plus Reznikov requests. Okay? So if we use now two very important theorems, which are the Köcher-Wimber theorem and the Jordan von Neumann and Wigner classification of Jordan algebras, we find the solution to our problem. Because Köcher-Wimber theorem says that every symmetric cone is isomorphic to the positive cone of a formally real Jordan algebra. So each time we deal with a symmetric cone, there is a certain Jordan algebra, formally real, that is hidden behind. And then, using the classification of all the finite dimensional formally real Jordan algebras, we have that in the case of three-dimensional Jordan algebras, we have only two possible Jordan algebras. The first one is the direct sum of R endowed with this associative Jordan product. And in the case of non-associative Jordan algebras, we have two perspectives. The first one is a matrix perspective, and the second one is a vector perspective. The matrix perspective is endowed with this anti-commutator, and the second one, the vector perspective, is called spin factor. It appears often in the analysis of special relativity issues, and it is endowed with this Jordan product. And these two Jordan algebras appear to be naturally isomorphic as Jordan algebras. As you can see, the isomorphism doesn't make use of any choice of basis of any structure. So they are naturally isomorphic as Jordan algebras. So if we compute the positive cone of the first Jordan algebra, we find exactly the first space that is allowed by the Reznikov theory. And if we compute the positive cone of the second Jordan algebra, we find exactly the other choice allowed by Reznikov. So Reznikov said, instead of dealing with two possibilities and all this set of axioms, Schrödinger, etc., we can use only one sentence and state that C, the space of perceived colors by a trichromatic observer, is the domain of positivity. We have to use also the closure, you understand why in 1 minute, is the domain of positivity of a three-dimensional formally real Jordan algebra. So I could have started with this axiom, but of course we would have known the relationship with color, but this is the starting point of our theory. We use just this axiom, and we only, the only thing that we add is that we analyze this axiom about the space of perceived colors on the basis of quantum theories. And this means mathematically that C for us is the state cone of a quantum system. What does it mean, state cone? It means that this is the space of states of our system modulo a real coefficient, non-negative real coefficient. Now I'm gonna tell you something about why we deal with a quantum system and why we introduce all this machinery. Sorry, there are profound reasons. I absolutely don't have the time. I'm sorry to introduce that, but at least the mathematical and the perceptual motivation of why we had the idea to study color through quantum theories, because it seems something that comes from the galaxy of Andromeda otherwise. So the mathematical motivation, I already explained it, is the use of Jordan algebras that is so natural in color perception and so natural in quantum theories. But there is also a perceptual motivation. It is well known that when we perform color matching experiments, we are in a dark room, we have one test light, and we want to match this test light by using 3 projectors, for example. If we prepare this situation in exactly the same manner and we repeat the experiments many times, then we don't have a single selection of these 3 lights that superposed produce the match, but we have a distribution of selections, a distribution which has a peak on the most probable selection. And this is highly reminiscent of the probabilistic interpretation of quantum measurements, okay? So I told you there are other reasons, philosophical reasons, experimental reasons, but I just want to introduce these 2 ones in order to motivate why we study color perception from a quantum point of view. In general, in quantum physics, if you read the books of Dirac and von Neumann, you always give definitions which are operational definitions and mathematical definitions. In a nutshell, I will introduce the operational definitions and then I will go through mathematics, because I want to show you how theory appears naturally in our model when we deal with a quantum point of view. So For us, the quantum system is just a visual scene in which we have lights that can be observed by a human being. And the operational definition of a quantum state is the simultaneous knowledge of all the possible measurements result about color observations, which can also be defined as an equivalent class of preparations of a visual scene. What is an equivalent class of preparation? For example, imagine that you have a patch and you throw light on this patch that you perceive with a certain color. And imagine that this light is neon light or tungsten light or LED light. Independently of the light that you use, if you say, I perceive the color in this way, then all these preparations belong to the same class, equivalent class. Okay, so this is just to tell you how the machinery of operational definition of state can be absolutely fit with color experiments. The object of measurements are called observables, and if we want a real quantum theory, we have to use a non-associative algebra, so we use this Jordan algebras, and the last definition that I need is that of expectation value, that is the average outcome of multiple experiments, measurements, sorry, performed when the visual scene is prepared in the same state. So now we go through mathematics and on a nice formal ground, and we see what mathematics of quantum theories allows us to say. Yes?
Just quickly before we move to this.
Yes.
Can you give an intuition of this operation you have on the algebra? What do they mean in terms of perception and so on?
What kind of operations?
Well, it's an algebra, right?
Yes.
It has a product.
Yes.
What does it mean?
We don't use, actually we don't. Yes. For example.
Yeah, exactly. It's just a mathematical thing, so it has a meaning on the level of perception.
Well, we use the Jordan product when we perform expectation values because we take the trace of we will see a density matrix product with the observable.
So it comes later.
In terms of?
It comes later.
It comes later. Yes, it comes later.
Sorry.
No, don't worry. Of course, if you have any question, please feel free to interrupt. Okay, so we will see. Actually, I didn't write it here, but it is, of course, a Jordan product. So now we use mathematics, and I will show you two things: how to interpret Newton color disk, that was the first geometrization of color, and then how the Herring theory emerges. I don't know what happened here. Oops, there is a problem, apparently. Okay. Not here.
So you mean that people can see these slides
un problema vostro, ok. È un po' un problema perché poi ho anche, cioè potrei farlo alla lavagna, ma ho anche delle immagini importanti a mostrarvi, quindi è un po' un problema. Ok. A posto? Posso continuare? Ok. Mi tengo lontano da ogni cavo. Ok. Okay, sorry about that. So finally, let's use mathematics to give a formalization of Newton color disk and also to show how Herring theory emerges naturally in this setting. So first of all, no, sorry, I advanced. This was the slide, the last slide. So states in the algebraic formulation of quantum theories are described by density matrices. Density matrices are in general denoted by rho, and they are elements of this Jordan algebra, and they are positive element of the Jordan algebra with trace normalized to 1. And if you do the computation, you can write a generic density matrix like this, and the parameters appear in a vector which belongs in the unit disk. And this is called in quantum theories the block disk. and it appears to be exactly the state space of the real analogous of what is called a qubit. A qubit is a quantum system that can be measured only in two states. For example, electrons with the two spins, or the state of polarization of a photon. Okay, but in order to study electrons and photons, you need complex quantum mechanics. Here we are dealing with real quantum mechanics, which is allowed. Real, complex, and quaternionic quantum mechanics is totally allowed. So we are dealing with real quantum mechanics. And the expectation values are written as the trace of rho Jordan product with A. And since we have parameterized the states with these density matrices in the unit disk, the most natural parameterization is the polar parameterization that we will use a lot. And a density matrix can define either pure or mixed state, and a fine descriptor of purity of mixedness is the so-called von Neumann entropy, which is the quantum analogous of the Shannon entropy. It is, no, again, please. I don't know, I didn't touch anything.
Ogni volta gli va ridetto.
Periodicamente? Ah, eccolo. Quindi ogni volta gli va ridetto periodicamente questo. Ok. Okay. Shall I continue? Okay, sorry about that. Okay, so a fine descriptor of purity or mixed of a state, and this is a crucial point, is the von Neumann entropy. Von Neumann entropy is a concave radial function which has this expression here, and we can define pure chromatic states in terms of von Neumann entropy by requiring that the von Neumann entropy is 0, which means that if you do the computation, the pure states are on the border of the disk, on the unit circle, and you can also compute the maximally mixed chromatic state, which is exactly parameterized by the center of the block disk, and the corresponding density matrices is 1.5 times the identity matrix. This allows us to give a formal mathematical explanation to what Newton wrote in his celebrated Optics of 1704. He introduced this color representation here. People who work in history of physics think that he introduced this representation inspired by Descartes' Cartesio representation of the division of octaves in music, but he didn't give any explanation of why he represented color this way. Still, CIE and all the people working in colorimetry use it today without any mathematical explanation. Now I'm telling you why we think that our theory gives a nice explanation of this representation. In the center, we have the chromatic states. On the border, we have what Newton called the spectral colors, which was the colors that came out of its famous prism experiments. And Newton said, between spectral colors, which are pure, and the center, which represents achromatic colors, we have colors with different saturations, with different purity. And he said, we just have to compute the distance between this and this. He didn't say Euclidean distance, he didn't say anything about this, but all the people used Euclidean distance, even nowadays. Instead of Euclidean distance, we claim that a better measure of saturation is 1 minus the von Neumann entropy, which has this expression here. And this is not based simply on the fact that we measure the highest and the lowest von Neumann entropy on the border and on the center, but also because this expression here coincides precisely with something that is used a lot in quantum information theory, which is the relative quantum entropy between the state defined by the generic density matrix and the achromatic state. And this allowed us, in one of the last papers that we published, to define a certain number of coherent definitions in which we use a lot the quantum relative entropy. So, of course, we have to perform experiments, and we are dealing with a group in Norway, and they are doing this kind of experiments to see if this fits our perception, but we believe that, at least theoretically, this is a much better definition than the Euclidean distance between points in the unit disk. Now, so in our opinion, we have formalized Newton color disk, and now I show you how Herring opponency emerges naturally in the quantum theory. And this is just a matter of representation. We just select the most simple, the simplest basis that we can choose for this Jordan algebra here, which is called the block basis, and it's composed by the unit matrix, the identity matrix, and the two real Pauli matrices. So if we choose this basis, it is actually an orthogonal basis, and being orthogonal, we can decompose the generic density matrix like this, and this is a notation that you use in every books of quantum physics, and the vector Vs is called a block vector, and the components of the block vector are exactly the expectation values of the two Pauli matrices. Let me recall that the two Pauli matrices belong to this Jordan algebra, so we have to consider them as observables. Then we understand what is the concept behind real Pauli matrices. So let me show you with an incredibly simple computation how Herring opponency appears in our model. So let's consider two pure states S1 and S2 with the corresponding density matrices, and these are the unit block vectors that are corresponding to these pure states. It is known that pure states in quantum mechanics are represented by orthogonal rank 1 projectors. They project onto rays U1 and U2. And let's ask ourselves when these rays are orthogonal. Well, there is a relationship that you can write between these rays and the block vectors, which is this one. You impose that these two rays are orthogonal, and in order to have orthogonality, the block vectors must verify this. Their scalar product must be -1. You introduce the polar parametrization, you do the computation, and you see that the orthogonality of the two projectors is written as the fact that the absolute difference between the angles is pi, which means that the two block vectors must be antipodal. Okay, so this is not something that is natural, because it only works in dimension 2 and 3. It doesn't work in dimension starting from 4 on. So this is a peculiar thing of dimension 2 and 3. Now we can use this fact to introduce Herring opponency. Why? Because in quantum theory, it is well known that orthogonal states represent maximally distinguishable states. So incompatible states, okay? So what are incompatible states in Herring theory? You cannot have a compatibility between red and green and blue and yellow, okay? And so this is incredibly simple how Herring theory pops out into our model. We simply have to choose the block representation. You write the Pauli matrix sigma 1 like this, and you can see antipodality. You write the Pauli matrix sigma 2 as this difference, so antipodality. You introduce this into the representation of the generic Pauli matrix, and let me discuss it in the next slide. You have, I think that we can all see this as a gray. So this is the contribution of the achromatic state, and this is the contribution of the two opponent states, red and green and blue and yellow. And look at the coefficients behind these contributions, and the coefficients are exactly the expectation values of the Pauli matrices. So the interpretation of the Pauli matrices as real Pauli matrices as observable is that they are the observables that deal with with the color opponency. Okay, and now we can complete even more our formalization of a Newton this, because we can set the opponent colors as antipodal points on the block disk. Okay, so this is yes. This it's totally arbitrary. It's blue. No. This is just a matter of names. So you choose the name blue and you choose the name yellow. But there are two sensations that are not compatible. Okay. But for example, you can also say instead of blue, you can say violet and orange, something like that. So you can switch a little bit the axis, but there are always two couples of opponent colors. The name that you give to this kind of opponent sensations is just arbitrary. Okay, we can discuss about it later, but it's called. There is actually a certain branch of colorimetry that is called color naming that deals exactly with what we are talking about. Why do we choose names about colors? You know that Icelandic people have 60 names for white or gray, so it is a matter of choice. But the fact that there are two couples of opponent color, this is not changed in any culture. Okay, but if you want, we can discuss about it later. Okay, so until now, it's just a formalization of known facts. Now let me show you the most interesting facts in our opinion. What can we do with this quantum formalism? The first thing is, of course, to try and see if we have Heisenberg-like uncertainty relations. We have Heisenberg-like uncertainty relations because if we define the quadratic dispersion of an observable like this, you do some computation and you obtain these Heisenberg-like uncertainty relations. Let me discuss what they mean. So here in the figure, you see a polar representation of the right-hand side of this inequality. And look at the fact that, of course, you know that when you represent it like this, you know that dark colors correspond, or dark intensity corresponds to something that is close to zero, and as long as you go to let's say more intense representation, you have, as you can see here, greater values of this quantity. So let's see what correspond black, that is a zero. They are exactly the opponency axis, which means that if we have colors that are positioned on the opponency axis, we don't have uncertainty relations, because we are simply saying that the product of these two dispersions is greater or equal than zero, which is of course true because they are two square numbers, okay? But if this is strictly greater than zero, we have uncertainty relation. Here, for example, this should be an orange, because this is red and this is yellow. This is an orange, and our theory says that if we try to simultaneously let's say understand what is the strength of opponency red and green and yellow and blue in order to describe a color, for this kind of colors here, it should be impossible to do it simultaneously. Okay, we are experimentally testing this with a group of Norway. The protocol in order to set up this experiment is hyper long, and so we don't have a test yet. But this is what it means. If we try to do what is called hue cancellation experiments in order to understand what are the two couples of opponent colors that describe a color, it should be incredibly difficult for these colors here, and as long as we approach these colors here, it should be very easy. So this must be verified. It's just a theoretical prediction. Let me now go to the final part of the talk. We want to use quantum measurement and quantum information tools in order to understand something different about colors. And there are two kinds of transformations regarding open quantum systems that we have analyzed. So first of all, why using open quantum systems? Open quantum systems are quantum systems that can interact with each other. And since we are observing colors, we are interacting with colors, okay? So we must use open quantum system, okay? A closed quantum system is just the color stimulus, but we want to interact with it. And also we want to be able to deal with the complex scenes with more than one color, okay? So we must use the theory of open quantum systems. And the transformation about states in open quantum systems are of two kinds. The first one is called Luder's operation. And the Luder's operation is a point-wise defined transformation. And it is the first one that I will discuss. And it reveals the relativistic nature of color perception. You will see Lorentz transformation appear almost magically using Luder's operations. And the second one is the theory of channels, and the theory of channels will allow us to study individual color spaces, and in particular, color deficiencies, daltonism, etc. So let's start with the first one, Luder's operation. Luder's operations are related with the concept of effect, and effects codify the probabilistic nature of quantum measurements. I absolutely don't want to introduce effect with the very simple matrix that will appear after this slide. Let me just use 30 seconds of your time to show you why effects are related with measurements. Otherwise, it seems to use something that is just a formal definition that we don't understand. So the very simple thing that I have to say is that in 1927, von Neumann did something that is great because he associated the concept of quantum observables with self-adjoint operators on a Hilbert space and also with spectral measures. And spectral measures can be associated with projector-valued measures. And no, you have to do it again. Per le persone che ci stanno ascoltando dobbiamo riaccendere il proiettore, quindi un secondo di pazienza. Ok, proiettore riacceso. Okay, so how these kind of projector valued measures are associated with measurements in quantum theories? Well, if you consider the Borel sigma algebra and a density matrix rho, then this transformation here gives you the probability that the measure of the observable A is registered in the Borel set B when the system is prepared in the state rho. This is one of the postulates of quantum mechanics, okay? The work of von Neumann was so great and so mathematically impeccable that it was written in stone until the 60s, late 60s, when Ludwig, Davis, and Lewis tried to deal with a relaxation of the request of von Neumann and showed that we can still deal with all the probabilistic setup of quantum mechanics if we require only positive operator valued measures and not projector valued measures, which means that E of B is a positive operator, and with respect to the natural order of the positive operators, this operator must be between the null operator and the identity operator, okay? And this element here is this positive operator here bounded between the zero and the identity is called effect. This is why effects are related with quantum measurements. So in our theory, let's come back to our theory. So from this huge, beautiful theory, we just deal with 2x2 matrices. In our theories, a matrix effect is simply this matrix here, which is bounded between the null matrix and the identity matrix 2x2. Using, you remember, this natural isomorphism between the Jordan algebras, we can also transform it in a vector that belongs to the spin factor, and it appears this effect vector that is written like this. So, what are the Luder's transformations? The Luder transformations are transformations defined on a fixed state like this. You take a state represented by a density matrix, and then you do the sandwich with the square root of this positive matrix that is the effect matrix. This is called Krauss operator, and it appears everywhere in quantum information. And take a look of the fact that this is not a state. This is a generalized state. Why that? Because if we compute the trace of psi e of rho, we obtain the expectation value of the effect on the state rho, which belongs between 0 and 1, and is not 1. But we can normalize it to obtain a post-measurement state just by dividing by this. But we cannot apply a Ludus operation on the whole space state, because of course the normalization would change for every state. Okay, this is why Ludus transformation are point-wise transformation on the states. If we look at these operations not with respect to the algebra H2R, but with respect to the spin factor, we obtain the relativistic nature of colors. Why do I say that? And this relativistic nature of color will also formalize a heuristic guess made by the theoretical physicist Ilmaz in 1962. So why do I say that? So this is the representation of states with respect to the spin factor. We perform the Ludus operation with respect to this, and look what happens. We find that if rho is a pure state, the transformation is this one. If rho is a mixed state, we have this transformation. Look what happens. We find the appearance of the Lorentz factor, which is exactly the Lorentz factor of special relativity when the velocity vector is the effect vector. And this operator has a matrix representation like this. And if you take a look at the matrix representation of Lorentz boosts with respect to a general velocity vector between two inertial frames in special relativity, it is exactly this one. So Ludus transformation with respect to spin factor representation are Lorentz boosts. How can we use this in our color theory? Well, we deal with adaptation here. Why? This is this is a quite difficult point. I hope that I will be clear. If you have any question, please ask. Our model is built with experiments performed by adapted observers. What does it mean? It means that we have a person that is in a dark room. It takes a look at a color stimulus after a certain time. In this time, his or her visual system adapts to the visual conditions, okay? And what does it mean, adaptation? It means that if we have an achromatic patch, this will be perceived as achromatic independently on the of the illumination that we use. For example, it is well known that I'm looking at the shirt of Maria Stella, I perceive it as white, independent of the fact that the illumination here is absolutely non-neutral. This is why, because I have adapted to this illumination. Color doesn't belong like this for cameras, because if you take a picture with your digital camera and you don't use a white balance algorithm, that is something that must be introduced as a software, then you will have a picture that reproduces the color of the illuminant. Okay, so since color measurements are represented by Ludus transformations, and color measurements in our model represent adapted observers, all this turns out in the sentence that if our theory is true, then Lorentz boosts should be able to be used to perform white balance transformations of pictures. This is where people who work in image processing use their pets. So let me introduce you to Panko. This is my cat. And I took a picture in my house. I don't know if you know this IKEA lamp. It has this shape. I don't know how to describe it in English, but has this shape with a lot of wood, and the color that pops out is a very orange color. Anyway, imagine this kind of lamp that I have in my apartment, and I took the picture here without any white balance algorithm in my camera, and what you can see is a color cast generated by this lamp. Okay, behind. The structure behind are the staircase of my house, which is not orange, is white, and also the mouth of Panko is not orange, but is white. So incredibly, we were very shocked when we used the Lorentz boost that pops out from this equation here, exactly this equation here, to write an algorithm to perform a white balance, and we obtained a white balance. So it's not that you wake up in the morning and you want to use the Lorentz boost to do that, but it works perfectly. So this, in our opinion, is an indirect proof of the fact that we are saying something that makes sense. Then, this is the last slide before finishing with the future perspectives. This is the last work that we have done with Michele Alde, who was doing his master at the University of Milan, and we completed the classification of a Rebit channel. The classification of qubit channels was known since 2012, but nobody classified the Rebits, maybe because Rebits are so rare to find in real systems, so they didn't. People were not interested. But since we deal with Rebit, we wanted to classify these channels. What is a channel? If we consider an open system with a system and environment, then a channel is a linear and trace-preserving, completely positive matrix, completely positive map between the space of linear operators on the Hilbert space S in itself. And completely positive means that not only C must preserve positive operators, but also its extension, which is C tensor product with the identity function on the ancillary Hilbert space HE. So the theorem that we proven says that we can write every Rebit channel like this. So these sigma channels are orthogonal channels that perform a conjugation with rotation matrices. And the most interesting part is this one, because it can be represented as an affine matrix. And of course, we have constraints. We have found 4 inequalities that must be verified by these coefficients here. But I don't want to introduce the inequalities. I prefer to introduce the region of admissibility of the parameters lambda. We take the unital case with the shift vector null for simpler explanation. And if we consider these inequalities, we find this region of admissibility. And you can see that depending on the position of the couple lambda 1, lambda 2 inside this admissibility region, the effect of the channel on the whole state space on the block disk will be to shrink the state space into an ellipsoidal region that can also degenerate in a segment like this. And our interpretation is that this represents color anomalies. You know that color deficiencies, in general we call it in Italian daltonism, corresponds to the fact that 1 or 2 or the 3 cones in our retina don't work properly, okay? And in general, we have this ugly representation of colorblind people or daltonism with pictures in which they are almost achromatic or bluish and grayish. And this is absolutely not real. This is not true. People with daltonism perceive a whole bunch of colors. Just they have problems in understanding the difference between colors with different saturations or certain nuances of color. And we think that our model, in which we shrink the total chromatic space into ellipsoidal region that can be, of course, that can have high eccentricity or not, depending on the degree of anomaly, is much more reasonable. We are dealing with ophthalmologists to understand if we can use this channel representation in order to study color anomalies. So I finished, just introduce very, very quickly future perspectives. So first of all, we have to perform experiments. We are doing this with, I told you, people in Norway. I know that in Sesto Fiorentino, there are people who can perform this kind of experiments. If you know somebody of them, please, after the seminar, tell me about it, because we are very interested to discuss and perform this kind of experiments with everyone who can be interested. And regarding the mathematical part, I think that this is something that can be interesting for you, because even if we know the final result of adaptation, we still have to model the temporal evolution of adaptation. And this is a very complicated issue, because in closed quantum mechanics, this is performed by either the Schrödinger equation or in the formalism of density matrices with the Liouville von Neumann differential equation. And for the open quantum system, there is the equivalent, which is either the Lindblad master equation, in which the Hamiltonian must take into account also the environment and the interaction between the system and the environment. And there is also another picture that is given by the famous Stein-Springer theorem. But there is a problem. In our case, what is the correct Hamiltonian to choose? It is absolutely not evident what kind of Hamiltonian should represent our color model. But, and this is a much more difficult problem, how can we model time evolution in a real quantum mechanical setting? There are very few works in the literature about real quantum mechanical evolution. In our opinion, the most interesting is the proposal of Wouters, because Wouters is one of the theoretical physicists that studied more Rebits in literature, and he proposed to change the I, which appears in a Schrödinger equation, with a coupling with something that he calls an auxiliary U-bit, universal bit. And what do we need? We need a square root of unity. And so we need something that behaves like the imaginary unit. And this is what he introduced as a U-bit. So this is absolutely something that is not simple to deal with, but is very, very exciting. And we also want to model this kind of situations that I told you before. If we deal with a chromatic scene in which we don't have the possibility to see only one color, but multiple colors, for example, this is the easiest situation in which we have a color on a background, how can we describe the fact that, I don't know if you see it like me or if you look at the screen, but these two disks are sending to us exactly the same physical information. But I believe that if I ask you if they are similar, or if they are identical from a perceptual point of view, you tell me no, because this is a yellowish green and this is a very bright green. So how can we understand this phenomenon from a mathematical point of view? Nobody did it before. And we want to use the formalism, of course, of quantum mechanics. And also, since we want to introduce multiple colors, one of my dreams is to perform a sort of quantum field theory, because we want to study this color distribution as a color field and study this with the techniques of quantum field theory, and so introduce much more geometrically related stuff, fiber bundles, etc. I did with my PhD thesis on quantum gravity, so it will be very, very nice for me to do. And the last slide, I promise, is how can we deal with a frequency theory of what we did until now. In quantum mechanics, you take the Fourier-Plancherel transform on L2 and you obtain the frequency picture of quantum mechanics. What is the equivalent of the Fourier-Plancherel transform in our case is absolutely not obvious. Of course, we believe that we should deal with much more abstract things, for example, study unitary irreducible representations of groups. But what are the groups involved? Luder's transformation do not form a group, form a zero group in the sense of Unger. Channels do not form a group, only unitary or orthogonal channel form a group. And so this is quite difficult to deal with. But if we use the formalism of fiber bundles, vector fiber bundles, the sections of vector fibers bundle form a group, an abelian group, and so maybe we can use that. we don't know yet, but this is something that we want to deal in the future. I think that you all know MadMats. This is a divulgation website in Italy, and this is free publicity for Roberto Natalini and Barbara Anelli. They asked me in 2001 and 2003 to write a series of 6 episodes about what I told you, very comprehensible for everyone. And this is much more from a historical point of view, and I work with historian of physics Valentina Roberti. But you can, if you go to MathMaths and you write, you type la matematica del colore, you will find 12 episodes about what I told you. This is a selected bibliography in case you want to have a closer look to what I told you. And of course, if you have any question, I will be glad to answer. Thank you. Forse possiamo chiedere anche online, non so. Non so come fare a non condividere più lo schermo.
Forse c'è Dario.
Interrompi condivisione.
Sì. Hi, thanks for the seminar. Sorry.
Dario, non ti sentiamo.
No, wait a moment, Dario.
Ma mi sentite?
Adesso sì.
Sì. Just a simple question, because it's very interesting, but there was this problem about hidden variables right in quantum mechanics that was ruled out by APR inequalities and stuff. Yes. But in your case, have you thought that maybe there's a hidden variable description of what you're doing using instead the quantum formalism?
Mm-hmm. So your question is, are there hidden variables in our model, or do you believe that there are hidden variables?
So have you considered that there may be hidden variables?
Not yet, because we want also to deal with quantum entanglement, of course, in particular to study this co-induction of the two stimuli in different background, and we want to try to deal it with quantum entanglement. And when we deal with that problem, we will also consider hidden variables.
Okay, thank you.
Thanks to you.
Probably something that I missed. Is your you showed a slide about the section of an eye, but
wait. Okay.
One of the first slide.
So
I'm asking: is the model built with the biology information?
So yes, the section of the retina.
Then,
okay. Yes.
Yeah. So it is. So my real question is: this works only for the human eye?
Yes. Yes.
Because I heard properly, I don't know if it's correct or not, that birds have 4 of these cones. So it is possible to adapt also for sight in general?
Yeah, we try to deal with this problem with embeddings of Jordan algebras, and we studied the embeddings of Jordan algebras in higher and lower dimensions, and we found something that it was very interesting, but we stopped there because we wanted to use quantum channels instead of these embeddings. But I think that one of the possibilities is to try to embed this model into Jordan algebras of different dimensions. In any case, they are all classified, so we can study this kind of theories with the Jordan algebras with different dimensions. But for example, if you study Daltonism with Jordan algebras of dimension 2 without introducing effects and Luder's transformation, etc., you find something that is not coherent with our findings. So we must mix these embeddings with different dimensions of Jordan algebras with the theory of Luder's transformations and effects. But in theory, it is possible to deal with different, and also not only birds, but I don't know if it's true, but in ophthalmology literature, there are works that talk about the fact that certain women have 4 cones instead of 3 cones. I don't know if it's true. There is still a huge debate about this, but it seems that certain women have a sharper color vision, and with the electronic microscope, in my opinion, they haven't found this 4th cone belonging to women, but it could be the possibility to do experiments. But the huge amount of experiments that we have, thanks to Maxwell, first of all, and all the other experiments that have been done, is on trichromacy and not in tetrachromacy or something about dichromacy, yes. But tetrachromacy, not yet. Thank you.
Other questions? Okay, so no. We thank you.
Okay. Thanks to you.